Welcome to part 2, which is going to be clinical applications of pharmacogenetics. All right, remember that pharmacogenetics is a set of variations in a population or in an individual that impact drug metabolism. The ways this can impact metabolism is with the uptake of drugs, the elimination of drugs, and the mechanism of action, or the pharmacodynamics. What this can lead to is variations in the concentration of the drug, which then you have variations in action of the drug. The type of variation really depends on the type of metabolizer the patient or the person is. You can get QT prolongation, which can lead to dangerous arrhythmias, fatal skin reactions, and there's a continuum from a single nucleotide, for instance, a T substitution instead of an A, all the way to multiple biologic pathways. This slide lists several drugs that are impacted, which you can read. You can pause the recording. And the fourth bullet point is the skin reaction I was telling you about. It is with one of the HIV drugs, abacavir. It is required that genetic testing be done looking for this HLA-B variant because the drug, and if that variant is there, there can be a potentially fatal drug reaction. If you remember, HLA stands for human leukocyte antigen, and it is a marker on cells. So this is looking for a specific drug reaction. Also, simvastatin myopathy is now linked to a gene variant that codes for a transport molecule. So when that transport molecule has this variant, the person is at high risk for simvastatin myopathy. Also, there are many receptor genes, particularly the beta-1, which is in the heart, and in a patient with heart failure, let's say we're giving them a drug to slow the heart rate, to improve contractility, and they have a cytochrome P variant, we're not going to get the effect that we're looking for. So the examples that we talked about in class, I just want to elaborate on a little bit for you. Codeine, as we said, is a prodrug. It must have CYP2D6 in order to be metabolized so that the patient gets some analgesia. In a poor metabolizer, think about what would happen with the usual dose. In nortriptyline, this is not a prodrug. It's given, it's taken in its active form. However, it needs CYP2D6 to be metabolized so it's cleared and excreted. If you have a poor metabolizer, what will happen with the usual dose? This slide begins to answer the question about the ultra and the poor metabolizers. So with the example of codeine, which is the prodrug, the ultra metabolizer is going to be quickly metabolized, quickly converted into the prodrug. So the expected area under the curve is going to shift. And the patient's going to say, wow, this snowed me at first, but in 2 hours, my pain comes right back. So really think about how that area of the curve is going to be in terms of the slide we had that shows the toxicity range and then the wear-off range. So the poor metabolizer, it's never going to get converted, and the patient's going to say, codeine does nothing for me. They might say, Vicodin is better. You might think that they're drug seeking, but truly, when it's pharmacogenetics, they're really telling you what's happening. And of note, Strattera, which is a medicine for ADD, ADHD, was the first drug to come out with a pharmacogenomic warning, and it's listed below, which you can read that. And it's about the side effects that occur with poor versus extensive metabolizer, and Strattera needs 2D6. Here you have a great diagram which shows codeine at the top, and remember what we talked about earlier, the type of drug it is, and nortriptyline on the bottom, and then the arrows indicate EM, PM, UM. Extensive metabolizer, now remember what that stands for, poor and ultra. So if you just study this, you'll see that the extensive metabolizer, which is also called normal or wild type, they take their codeine, they have their 2D6, it gets transformed into the active metabolite, they get pain relief without adverse effects. Please pause the recording and study the poor and ultra metabolizers. Same thing with nortriptyline, which is not a prodrug. So the poor metabolizer is going to be the kind of opposite of the poor metabolizer in codeine. So just take a moment and study that and think about what is happening in terms of pharmacogenetics and metabolism. A bit more about CYP2D6. This is the one with the greatest degree of genetic variability. Some of the substrates are listed for you. Remember, the substrate is a drug molecule that is acted upon by an enzyme. So codeine, because it's acted upon by 2D6, is a substrate of 2D6. It's a prodrug, as we said earlier. Fluoxetine is not a prodrug, but it's also a substrate. So the pharmacogenetics, if there is a variant, is going to depend whether they're an ultra metabolizer versus a poor metabolizer. This is another great slide for you to study if the impact of the poor and ultra rapid metabolization makes a difference. This talks about whether the enzyme activity is decreased on the spectrum all the way along to markedly increased. The clinical or therapeutic effects are going to depend if it's a prodrug or not a prodrug. So you might want to pause and study this for a moment. Across the top of the slide, we've got the three most common variants in polymorphisms, from ultra-rapid to normal, which is called extensive or wild type, to poor. Those are the three most common. 2D6 has over 90 allele variants. 2C19 is also highly variable, and this is the one where you can get the reduced function with clopidogrel, and we can call those a non-responder. 2C19 polymorphisms are going to impact clopidogrel, citalopram, and the TCAs, or tricyclic antidepressants. Clopidogrel is the prodrug, the other two are not prodrugs. So slow metabolizers of citalopram or the TCAs only need about half the dose of a normal metabolizer to become a therapeutic. Genetic testing, screening for these variants is very, very helpful. Here we see the types of mutations on the 2C19 gene. Remember, the star allele, the star indicates the locus of the variant. So you can have star 1, which is the wild type, normal, or extensive. Those are all the three interchangeable terms. Star 2 is the most common loss of function, and this tends to segregate mostly in Asian populations. So you kind of have a heads up if you have an Asian population patient, that if you're going to give them clopidogrel or a TCA, clopidogrel you might want to consider testing. TCA, remember, if they are a poor metabolizer, they're going to be really at risk for toxic effects. Star 3 is in less than 10% of the Asian population. These can also appear in non-Asians as well. Here you have some specifics on the 2C19 gene. It has 9 exons, so pause a minute, try to remember what an exon is. It's situated on chromosome 10. More than 30 SNPs have been identified for it. A little more information on clopidogrel, which, as you know, is an inactive prodrug, but it's rapidly converted to its active form with transformation in the liver. Remember, we've got phase 1 and phase 2 biotransformation, which we're going to talk about in a little bit. And the mechanism of action, or the pharmacodynamics of clopidogrel, is it inhibits ADP-mediated platelet activation and aggregation. So it binds to the platelet receptor, the one that's listed right there. So it's a platelet inhibitor. I wanted to show you the image that shows the exons, because we just talked about the fact that clopidogrel has 9 exons. Just a picture of interest. Exon is the coding the codable portion of the gene. With the drug clopidogrel, after it goes through phase 1 as well as phase 2 biotransformation in the liver, about 15% of it is active drug, and this metabolism is critical to successful treatment. So genetic variants have a high impact on our clinical or physiological response to clopidogrel as a platelet inactivator. So we can have either normal, reduced, or absent enzyme activity, or we can actually have a gain of function, which is an overactivation. This slide is showing the biotransformation or metabolism of clopidogrel. As you can see, it happens in 2 phases with number 3 arrow there indicating when it actually binds. So moving up to number 1, this is phase 1 biotransformation, which is also where oxidation happens. You can see that 7 enzymes are required to activate clopidogrel. So it's kind of taking a village here. The enzyme of interest in phase 1 is 2C19, which is the one with the many different polymorphisms. So phase 1 is oxidation. We need all those enzymes. And then we move down to phase 2, which is conjugation. What I'm referring to is the class lecture on the metabolism or biotransformation of drugs happens in 2 phases. So phase 2 needs 4 enzymes, particularly 2C19 and 2C9. Of those have a lot of genetic variability. So once we get through phase 2, we now have active metabolite, which is about 15% of the original dose. Number 3 there is where the active metabolite binds to the platelets, rendering them inactive. This is pretty cool. This is the actual, I took a screenshot of the package insert, the prescribing information for clopidogrel, which was updated in 2016. And you can see where the language, it talks about how it needs the active metabolite and if there are non-functional alleles in the 2C19 gene. So just take a peek, read that over. You can access this information online. You can also kind of get a summary of it in your Hippocrates. All right, so this shows the distribution of possible mutations in people, their metabolism of clopidogrel. You can have the poor metabolizers, so this is going to be your loss of function, and they're listed. Remember, star 2 means they got this allele from both their mom and their dad, star 2, star 3, or star 3, star 3. The other one that you can see is that there's ultra-rapid metabolizers, extensive. Now think a minute, what is an extensive metabolizer? Or the intermediate metabolizers. So just take a minute, kind of study this, see what can happen. To summarize, many things can impact therapeutic outcomes, but particularly in this first unit, we are considering pharmacokinetics, pharmacodynamics. This presentation speaks to pharmacogenetics. We're also looking at how age and lifespan impacts therapeutics. We're looking at drug interactions, the inducer, inhibitor, single nucleotide polymorphism. This wraps up this presentation. Here is a reference slide for you, and there will be questions on this presentation for you, and those are for credit. So I hope you enjoyed this. If you have any questions, please send me an email. Thanks for your attention.